Hello, welcome back, I guess, to the YouTube channel lectures for Geog 300 for our unusual pandemic times. The next topic we have is linear regression. So I don't have the framework up on the board yet, we'll get to there. But first some background and some of the motivation. In terms of regression, as it relates basically to chi-squared, you may have gone through chi-squared thinking its purpose is making predictions, yes, making prediction. But what we did in the labs, especially of taking a group average and using that to generate the prediction, you might have been thinking there's got to be a better way. And indeed, linear regression can be that better way. Linear regression is, or any kind of regression, there are many kinds of regression. We'll focus on linear here. Linear regression is probably the most commonly used statistical technique there is. And if you broaden this out to other forms of regression, it is definitely basically the statistical workhorse of so many kinds of analysis. So it is quite important to recognize what regression is, what linear regression is, and how it generates these predictions that we can use. So, to be even more precise in that comparison, so we have chi-squared and it's comparing the predicted against the actual value. As we saw, we can generate that in many different forms. But the assumption, in a way, is as the prediction goes up by 1 unit, the actual value should go up by 1 unit. They are to track each other precisely. Now, for coming up with, as we did, predicted values by just taking a group average, comparing, say, a categorical value against the numerical value at the end. So the categories group average for each category, using that to generate the prediction. For linear regression instead, what if instead of a categorical value, we had a continuous value, a continuous variable? So instead of being, okay, I'm going to classify all counties by high, medium, and low income, and compare that to the poverty rate, the average poverty rate in high income, medium income, and low income counties. Why not just directly comparison and do away with that intermediary step of generating the prediction in the first place? You may, in many cases, and it'll come up in labs and in software, you may see the acronym OLS for ordinary least squares. It is basically how linear regression works. So if you see OLS or ordinary least squares, it's the basic form of linear regression. So OLS regression, you are allowing a broader set of comparisons, but they have to be continuous variables. So income measured in dollars, poverty rate measured in percent. But what we can do is not a one-to-one ratio. As for chi-squared, as our prediction increased one value, we're going to have some problems in the outcome if the actual value didn't also go up by 1. In regression, if I increase the median household income by $1, that's probably not going to decrease the poverty rate by an entire percent. $1, probably not that big of an effect. But there's probably some very tiny effect for each dollar. And that adds up, and that adds up until you increase the median income by $10,000, you do have a noticeable effect. So it doesn't have to be 1-to-1. It can be 10,000 to 1 and still work. The other thing is, as the prediction increases in chi-squared, so should the actual value. They have to go in tandem. As one goes up, the other goes up. In regression, it can go either direction. So the relationship can be as one goes up, the other goes up. Typically, as the percent of a population in a county with a college degree increases, so does the median income of that county. So that's a positive relationship. We can have a negative or inverse relationship. As one goes up, the other goes down. As the income increases, the poverty rate, we would hope, decreases. OLS regression is ultimately measuring the strength of this relationship. And in a way, circling back, how well can we use that relationship to make some kind of prediction? So the next set of ideas here is linear regression is measuring conceptually, if not mathematically, conceptually a relationship between two variables. And this relationship has a direction. There is an independent variable which can vary, it is independent. It can vary as it pleases. We just kind of assume that its values are as they are. Meanwhile, we have the dependent variable. It is affected or controlled by the independent variable. So, in what we had before, we can say income is dependent upon education. So as the percent in a county with a college degree increases, the income is increased by that because those college graduates can have better jobs. The other example I had for the inverse was the poverty rate and the income. In this case, income is the independent variable. So we can have the same thing be in different situations, dependent or independent. We can say income is dependent upon education, but poverty is dependent upon income. So as income varies, then the percent living under the poverty line, the percent of the population living in poverty in that county, is going to, as income increases, it should decrease. The main caution there, as I have written here, it gets back to one of those earlier ideas in the pitfalls in reasoning. If you find two things are related to each other, you can find a relationship where as one goes up, the other goes up. That does not mean one must be causing the other. I believe I gave this example before while we were still meeting in person, but it's a good example here as well, where somebody went into finding the things that correlate with crime in English communities. And it so happens that the number of vicars or priests was correlated with crime directly. So that as the number of priests or vicars went up, so did the crime rate. Now it turns out that just because they're correlated does not mean that one causes the other. It does not mean that the vicars are the ones going out and robbing their parishioners. What it instead means is that in urban areas there was more crime, in urban areas there were more churches and therefore more vicars. So it did not mean that one was causing the other, even though they were correlated. So even though regression is building in and working with this implicit relationship of the dependent variable, its changes are based, at least in part, upon changes in the independent variable. When it comes time to do the write-up, don't just blindly assume that one must be causing the other. So visually or graphically, the basis of regression can be illustrated in a scatter plot. So we have along the horizontal axis, we always have our independent variable. And on the x-axis, the vertical axis, the y-axis, the vertical axis is always going to have the dependent variable. And what this starts with are the points. So for each county, where in this scatter plot would it lie? So we have our points. The concept of linear regression and why it is linear is we want to model or represent this relationship between the two. We want to have some kind of mathematical understanding of how the two variables are related. And that comes through drawing a line through that scatter plot. But as we'll see, it's not just any line. So I have a line, and this line, we have a few components to it. You may recall from high school geometry. You would have probably seen something about y equals mx plus b. In regression, we do tend to use something slightly different, but it's the same ideas. Beta and alpha. Sometimes the alpha, sometimes you'll see alpha, sometimes you may even see a beta with a 0. They would mean the same thing, just a different term for it. The beta here is the slope. You may also see or hear the term coefficient. So that is the coefficient in the equation measuring that relationship. So the coefficient is basically answering the question of, if I increase x by a unit, remember x here is the independent variable. As if I increase the college education percent, what then happens to the median income? As shown here, it goes up. So 1 unit here $19 is associated with, that might be around 52,000. And 20% college education rate might be related to 57,000. That means increase in one here leads to an increase here of, say, $5,000. So 5,000. But to know how to model this or to make a prediction, we also need a starting point. I can say, well, as I increase the college education rate, income goes up by 5,000. I cannot get any kind of meaningful prediction, however, if I don't know what the income should be when X, the independent variable, college education rate, is 0. We may not encounter any counties like that. Kind of like with ratio data, 0 here is meaningful in terms of the modeling at least, even if we never expect to encounter it in practice. So as the intercept in your geometry class, you may have called it the y-intercept. It's the value of y when x, or the independent variable, or in this case, college education rate, is 0. I can essentially do this with any line here. That still doesn't get me to linear regression itself. There's some special properties of that line which allows us to say it is the best possible line to go through those points. We get there through what are called the residuals, or the error in our predictions. So what we do to first measure the error, the math in terms of how we get the best line, again, we'll let the software handle that. I have a value here. Its college education rate looks like it might be about 28%, the way I've drawn it there. If all I knew is that the college education rate is 28%, I'm going to take where 28% lands on this line if that county is C, here's where I'm predicting the income of County C, what it should be, if all I know about it is its education rate. However, its actual value is much higher. So my prediction is too low. This distance, whether you look at it over here or over here, it's the residual or the error in that prediction for that value, or for that county, for that observation. Since that error is pointing down, it's negative. Our residual is negative. I had to, basically I overpredicted, or sorry, I underpredicted where it was. I can instead have a prediction that's off in the other direction. Where, based upon the income, or based upon the college education rate, I would think this county needs to have a bit more of an income than it does. This could be a college town, where, yes, especially with the faculty, there's a very high education rate. However, the presence of these students, who typically have much lower incomes, pulls this down. On the other hand, that could be a town with a high-end factory where there are people who can get very good paying jobs without a college degree. So there could be reasons for each county to have the errors it does. But based upon just the education rate, that is our prediction along this diagonal green line. The error we have is how far off each of our actual points is from that line by going straight up or straight down to have exactly how much prediction error there is. So geometrically, when we say this is the best line, if I take all the residuals for every county in my data set, square them, find the sum of those squares. The lowest possible sum is our regression line. So that's the sense in which we say is the best prediction, the optimal line. It can do the best prediction with the smallest overall residuals. In Geoda, we will not be doing this, but it is possible, and I have it illustrated in the slides, which include Excel, to illustrate we are not beholden to just linear regression. Looking at this, we might say that something that's a little bit curved would be better. So the orange isn't showing up all that great, it seems, but the orange line there showing maybe that's going to do actually better than the green straight linear line would be. However, because this kind of interpretation, as I increase X, as I increase my college education rate, what happens to Y? It's a constant amount of increase, very easy to understand. In the linear form, when I start to bring in a curve, it's harder to understand and harder to interpret. So, as you can see here, we will get this coefficient, we will get the intercept. There are two more numbers, so to speak, that we'll be getting from our regression that are important. So, in terms of what we get as output, we already saw we have our coefficient. We'll get our intercept. The next thing we'll see is something called r squared. Well, r squared is as x changes, how much of the variation in y is explained by that change in x. So, in a way, it's an overall measure of how good our predictions are. This is where, in a way, it's related to chi-squared. I mean, it's not that exact statistic, but it serves kind of a similar function in measuring how good our predictions are. So, if my regression line is flat, as I have it here, r squared is 0. There is no relationship at all. That is just a cloud of points, it's a blob. I'm just saying, really, I'm going to guess for my prediction that it's the intercept all the way across. There's no information in this. X has no bearing whatsoever. So here, for a kind of a moderate, a decent regression, where I have r squared of 0.5. Now, interpreting this, I can say about half the variation in y is explained by x. This means, because there's now a slope, the coefficient, or beta, is no longer 0. If all of the points lie perfectly along the line, then my r squared is 1. It is a perfect prediction, 100% accurate. So in a two-party system, if you tell me the percent for one party, the Republicans, I can predict with perfect accuracy how many voted for the Democrat. Everyone else. So that would be a perfect inverse relationship. Again, the coefficient isn't 0. Notice I'm not really making any statements for any of these about what the intercept is. It's there for mathematical purposes. There might be the occasional situation where it's useful for interpretation, but for the most part we ignore it. And lastly, I said there are 4 values. We have the coefficient, the intercept, our r squared, and of course we have a p-value. We've seen this before, you were probably expecting it. We have our p-value. So the p-value, probability that the data supports the null hypothesis. Again, the null hypothesis of nothing interesting going on, meaning there's no relationship, meaning beta is equal to 0, meaning that r squared is equal to 0. You will get in a standard linear regression with one independent variable, this is what you will get. So having set this up, I can now take linear regression and put it into that framework that we had worked with before. In the terms of identifying a question of what we're studying is basically boiling down to, is the dependent variable, whatever that is, related to our independent variable? The null hypothesis that there is no relationship, the alternative hypothesis that there is one. Notice here, the alternative hypothesis could be a positive relationship. As one goes up, so does the other, education and income. Or it could be inverse. As one goes up, the other goes down, income versus poverty. Really, we can treat the r squared value and the beta naught, the intercept. All three of them can be what we're considering our statistic. In the example that I have here, in the setup here of one independent variable and one dependent variable, where we can more or less ignore the intercept, because it's typically not part of our hypothesis up here, and work with either of those, and they would give us the same answer, the same information. Under the null hypothesis, r squared should be 0, beta should be 0. They do again form a distribution around 0. So it is ultimately something centered on 0, but if it's a little bit above, a little bit below, not going to not going to immediately throw it out if it's like 0.001, for example. And we see through the p-value, it's a probability there isn't a relationship. The probability r squared could be 0. Ultimately, recognizing that our points could have some level of error in them, or for some other reason, yes, we get from our sample, if we treat these points as a sample from a larger population, our sample gives us that particular line. The line for the entire population, however, could be a little bit steeper, a little bit shallower than that actual line. Do those guesses ever essentially become flat? If that becomes flat, then there is a chance that our relationship is not really there. We go through, we get our p-value here, probability there isn't a relationship, and however we get it, or whatever threshold we choose, we decide, do I want to take action or not? So I might decide, okay, at what point do I acknowledge or believe that really there is a relationship between education and income, and say invest funds from the county or from the state to encourage people to go to college, to help pay for college, trusting that that will have a return on that investment as those people earn more income through their degrees. So there are some other forms of regression, as I said. We'll see those next week. The last thing here for interpretation, it's a very frequent mistake I have seen people do in trying to work with and understand regression. The coefficient can basically be anything. However, r squared and the probability, the p-value, both range between 0 and 1. However, they are interpreted differently. An r squared of 0 means there is no relationship, whereas as r squared increases, the strength of that relationship gets stronger and bigger until once we have 1, it's a perfect relationship. On the other hand, recognizing that P is the probability the null hypothesis of no relationship is true, if P is 0, there is 0 probability the null hypothesis is true. That means there's a strong relationship. And as P increases, our belief in the null hypothesis is going to decrease until we get to a p-value of 1, and we are 100% confident there is no relationship there. So even though r squared and p are in the same 0 to 1 range, they are not interpreted the same. And that is a very, very frequent error I have seen, and as we'll go into the lab, into Geoda, we'll see working with the 4 values, especially the 3 of the coefficient, the r squared and the p-value, relating them one to another, and we'll see as you get further into the report how those can be presented and how to interpret those values. Future weeks, next week, we'll build upon some of the regression ideas that we see here into adding in a little bit more complexity and a bit more geography. And lastly, don't forget, there will be a test that I will put up in eCampus on Friday. Regression here is fair game. It will be on that test. So again, I hope everybody is safe at home, is still healthy, that everyone's family members are healthy, and they're all taken care. So until the next video,